All right, so this is called the Nelder Mead Simplex algorithm. And it's for optimization, okay? And the way this works, in this case, for optimization is, we're using it to find basically a minimum, okay? So we're going to try to find the minimum of a function, and the way it works is so I'll illustrate it for you. And if you want to use it to find the maximum of a function, you just take the negative of the function and apply the same algorithm, right? So max of negative of the function. Okay. So what a simplex is, a simplex in 2 dimensions is a triangle. Okay? And a simplex in 3 dimensions is a tetrahedron. Okay, so we have a triangle here, and then in 3 dimensions you've got something that looks like that. Okay? And so in a simplex in n dimensions, has n plus 1 extreme points or corners, and non-zero area or volume or whatever the n-dimensional equivalent is. In 4 dimensions, is it still called volume? What is it?
Hypervolume.
Hypervolume?
Yes.
Okay, well there you go. All right, so it has non-zero area, volume, or hypervolume. So there you go. Okay, so and this is what we have. So we start off. So I will illustrate how this works in 2 dimensions, which is how you will be. Which is how I imagine you will implement this, the problem that I'm going to give you guys on the final. Okay, so let me. So here I've got a function of 2 dimensions, a function x and y. So here I can write this, and it's x minus y squared plus x minus 2 squared plus y minus 3 raised to the 4th. Raised to the 10th power, okay? And then, and I'll graph this. Maybe I'll put in more than. And so here's a contour plot of our space. Okay? What are my options on contour? N levels equals 10. And let me just try. Yeah, I don't know what's better. Okay, well, we'll try this. All right, so here's a contour plot of the function. Okay, and so you can kind of see, this. You guys are all familiar with contour plots, right? It's like if you have this 3-dimensional shape and you're dipping it in water, and you draw the circles to show things. So this this boundary all is 1, and then you can see as the things go out, it goes 2, 3, 4, 5, 6, 7, 8, and things like that. And so we're going to try to minimize this function. So it's going to be somewhere inside here is what we're looking at. Okay. Okay. So let me copy this image. Actually, let me get the. And so the way the Nelder-Mead algorithm works is you start off with a triangle. Okay, you just kind of start off with 3 arbitrary points, and these form a triangle. So let's say you start here. Okay. Okay, this is supposed to be a triangle. It's really hard to draw straight lines on this tablet thing. Okay, and what you do is you label these points u, v, and w, so that f of u, the function evaluated at point u, is less than the function evaluated at point v, is less than the function evaluated at point w. Okay. So in this case, this one is w, this one is v, and this one is u. Okay? And then you're going to propose basically a few different points. Okay? So so right now u is the best point, and this is the worst point. Okay. Okay, and so I'm going to draw a few proposals here. So one is you take the line connecting u and v, and you find the midpoint there, and you reflect w across that midpoint so that it forms basically a parallelogram. Okay. So you take so this point we will label R for the reflection point. Okay, so it's reflected across across this. Okay, and then you evaluate the thing at R. Okay. And if this is an improvement over the best point, so if f of r is less than f of u, then that means you're stepping in the right direction. Okay, and so we try our luck again, and we try an extended point. Okay, so we're kind of like pushing our luck a little bit. Okay, and so what we do is we take this distance and we basically go out that much again. Okay, and this is the extended point. All right. So I mean, I could draw this, but basically you're just see. So R is the reflection across the line UV. Okay. And then E is you extend that, and you see, is this even better? Okay. So then you quote press your luck. If this is good, we try to press our luck. And try point E, the extended point. Okay. And then in this case, and then so if f of E is even better, okay, okay, then E is even better. Okay? And if it's not, then we stick with R. Okay, so in this case, E is even better, then E is even better, and then we take E. All right? Otherwise, keep R. Is that okay? All right, and so in this case, E is better than, we started off with W. U is our best point. R is better than U, so we would like that. And then we try E, and that one's even better, and so we're going to keep that right there. Okay? So that forms, so now we have 3 new points. Okay? We have E, U, and V. Okay? And then we relabel these U, V, W. All right? And then we try the algorithm again. Now, what do we do if R is not better and E is not better? Okay? So so this could happen eventually. Let's see what happens. So once you get getting near the middle zone, R or E might not necessarily be better. Okay. So let me save this. We'll go to the next slide. What do I want to do? Okay. Yeah, let me get rid of this. Okay. So let's just, I'm going to just draw the triangle. Okay, so this is a new triangle here. Okay, so right here, this will be U. This is our best. This is V, and this is W. This is our worst point. Okay, so we tried the reflection, okay, across the midpoint here, which basically forms a parallelogram. So that's point R, okay? And then if the function at R is better than the function at U, then we press our luck and we extend this, okay? So we basically take this piece and this spot is E, okay? And if f at E is even better than f of R, accept E. Otherwise, take R. Okay, on the other hand, if f of R is better than f of V, then that means I'm sorry, if f of R, sorry, I gotta think of my my line here. Okay. So let me just draw a vertical line over here, kind of evaluating right here. All right, so okay, so if R is better, then you try that, and then if E is better than R, then you accept that. Okay. On the other hand, if the reflection is in between V is greater than V, Okay.
So how do you define better? Is it higher or lower?
Yeah, lower. So so what we're trying to do is we're trying to minimize the function. Okay. Yeah. Okay. So if we're gonna we try these other things. Okay. So if f is better than u, then we extend that, and if not, if f is f of r is better than f of v, but not better than f of u, okay, then we can just replace f of w with f of r, okay, and we can continue the algorithm. On the other hand, if we're not getting improvements, then we can try a few other options, okay? So one is to we have the contraction. So I'm going to take this diagram here. Okay, so let's say this is not really an improvement. You know, it's coming out somewhere like here. Okay, then we propose this point here. Okay, and so this would be called the contraction point. Okay, so this is f of c. So this is if f of r is greater than f of v, then we try the contraction f of c, okay, and then we test, is f of c better than is f of c better than f of v, or is and then we also try the other contraction. So rather than going the full reflection, we try these 2 points. So I'm going to call this f of c1 and f of c0 here. Okay. Okay, and then and basically we're trying to just improve the 3 points of our triangle so that at every iteration the worst point gets better. Okay, so if if these ones aren't better than f of v, then we try these ones. Okay, and we're hoping, basically, we want to replace the worst point with one of these points and these ones we're hoping are better than f of v. So basically, we're trying to play kind of leapfrog with the points. Rather than just getting w better than, rather than just closing the gap between w and v, we're trying to get w to at least play leapfrog with the second worst point. Does that make sense? Because otherwise, our triangle's not going to get better, and we would just end up shrinking the gap between f of w and f of v. So we want these to switch places so that we're always gaining some kind of improvement. Okay. All right. So we try these ones, and we take whichever one is better, so that at least the new point is at least better than the second worst, currently existing second worst point. Okay, so we take the kind of the best performing point. Okay, and there's also the possibility that everything we've tried so far, C1 and C0, so that maybe this one is not an improvement over the worst point, or this one's not an improvement, and neither of these are improvements here. Okay, in that case, we if all else fails, we just shrink the triangle. Okay, shrink everything towards the point U. Okay, so step one, we do this. Step two, if this works, then we try that. If these didn't work, then we try these contracted points. Okay, so and then if all of these fail, okay, so if all other proposals fail, we shrink the triangle. Okay, and for that, okay, this involves changing both points W and 3. So we, W and V. We shrink V down to here, and we bring, W and V down to here and here. Okay, and so our new triangle is going to be the smaller one. So the shrinking generally only happens when you start to close in on the minimum zone, okay, or the small zone. And then so now that we've shrunken this, we're going to have 3 new points. So at the end of these, at the end of any of these things, you're going to replace the worst point with one of these proposal points. Okay, so that's for any of these 3. And if all of these all of these proposed points do not outperform the second best point, then you shrink the triangle. Okay, so what we're hoping is that all of these, so ideally, one of these will outperform at least the second best point. Okay, it's best if it outperforms the best point, but if it doesn't, we're hoping that it at least outperforms the second best point. And if that's the case, you replace the worst point with the proposed point, and then you'll have 3 new points, or another triangle, and then you continue the algorithm again. You have 3 so you're going to have a triangle. You basically propose a new point to replace the worst point, and you get a new triangle, and then you continue on. And if all of your proposed points don't work, then you shrink the triangle. So you're going to replace both W and V with new proposals. You shrink it, and then now you have a new triangle to continue the algorithm. Okay? Yes, question?
Were the initial points of U, V, and W chosen at random?
Yeah, they're kind of arbitrary. The initial points, they are arbitrarily chosen. If you graph this, you can pick wherever you want. And you go through this, okay? So let me just kind of write a few summary points. So at each iteration, you have a triangle, okay? The best performing point f of u, okay? Alright, I'm sorry, the best performing point is u, meaning the function evaluated at point u is the lowest among the 3. Okay, and then the worst is W, okay? Okay, and then we propose new points that can be used to replace W. Okay, all right, and then we hope the proposed point at least performs better than V, the second best point. Okay, and then the proposals are propose R, the reflection, propose E, the extension, okay, propose C0 and C1, these are both contractions. Okay, and then if all proposals fail, shrink the triangle towards point U. Okay. Does algorithm kind of make sense in terms of what it's doing? Yes.
So when do we stop?
So you stop after a certain number of iterations. So when you're doing this, it should improve. So you can stop after a certain number of iterations, or you can just see is once the differences between basically if all 3 points of your triangle have practically the same value when run through the function f of u, f of v, and f of w, they're all quite small, or the differences between them are all quite small. You can stop there. Okay, so there is like kind of a convergence criterion. Okay, so there is a convergence criterion. Okay, but or stop after a certain number of iterations. Okay, and so so I think for the final exam, I'm going to have you at least create a way to propose these 4 points, and at least evaluate them and whatnot. So I'm trying to decide how much I should have you guys code and how much I should have in the framework. So so that will be good. There's a there's lots of stuff on the Nelder Mead algorithm. This is a very good explanation. I'll post a link to this document. It's also covered. Let's see, a few other places. I mean, you can just type in Nelder Mead on in Google, and it's been implemented in R in the function optim. Okay, but we can use this for all sorts of applications. Okay, so so let me just kind of demo how this works in R, and and how it could be used in different statistical applications. Is that a question? Okay, no problem. All right. Okay, so here for the function optim, I had to redefine the function rather than a function of x and y. It's just a function of x, but there's going to be two parameters in x. So I have x1 as x and x bracket 2 as y. Okay, so this is the exact same thing as a function of x. And then there's a function for called optim, which just says optimize x, and I just give it an initial point 0, 0 for x, and I say do that. Okay, the true value, the true minimum, is at 2.25, x equal to 2.25 and y equal to 2.5, and if I run it, it's done. It's very quick, and it has found the optimum point at 2.250 and 2.500 644. So it's very good, and we can plot. I'm sorry, points, and we want to do the results, and we'll put that right there. Is that not? Did I mess something up here? All right, let me just redo my contour here. Okay, so right there is the minimum according to the R optimum function. Okay, so this is the lowest point that we have here. Okay, any questions on this? Let me just kind of show you an application for, let's say we wanted to do least squares regression. Okay, so let's. I'm going to just create a silly data set. Okay, so I've got 4 data points here, and then I can create a model, a linear model between y and x. Okay, and this is our line of best fit. Okay, and let me do M1 coefficients. The coefficients are intercept of 1 with a slope of 1.6. Okay? We can think of linear regression as trying to minimize. You guys remember what linear regression does? It tries to minimize the sum of squares residuals, right? So linear regression tries to minimize the sum of squares residuals. Okay, so the residuals, so we can create a function for the prediction. Okay, so the let's see, we'll call this P. P is going to be a function of basically B0 and B1, our intercept and our slope. Okay, and so the function B0, B1 is going to return B0 plus B1 times x. Okay, so actually it should be a function of B0, B1, and x. And then the residual is going to be the difference between, is a function between y, x, y, and p. and this is just going to be y minus the prediction p, right? Okay, so then we can start off with, we can say our beta vector, we can start off as 0, 0. So actually, let me change the formatting of this to be a function of b, and this will be okay, and so and then here, let me, oh gosh, this is going to be a slight mess here. So the residuals, we want to minimize the sum of squares residuals. So the function that we're going to try to minimize will be our residuals squared. So it's going to be squared residuals, which is going to be, we're going to do y minus p quantity squared, and then we want the sum of this, right? So this is the function that we're trying to minimize. I'm going to put the function to calculate the predictions inside here, and so this will just accept our parameters beta, okay? Because we have because of scoping, it will, if it doesn't find the it's going to look for x and it's going to look for y. All right, so let's just test this out. So we got x, y. This is our function. So b is that. Let's try square root of the residuals with our current parameters b, and that's 400. If we use the if we say b is 1 and 1.6, this should be our minimal sum of squares. Is that not right? Y minus p? This is too small. What did I do wrong? b1 plus b1x, b2. Okay, let's try this, sorry. All right, 1 and 1.6. Okay, that is the correct sum of squares residuals. Because if I ask for m1, let me just m1 residuals, and if I squared these residuals and sum them up, this is what we get. Okay. So anyway, so what we want to do is we want to minimize this squared residuals function, so I can just do optimize this function, squared residuals, and we'll start it off at 0, 0, and we're going to optimize the squared residual function, okay? So if I optimize this, I'm hoping, indeed, using the search algorithm, it finds the parameter for the first thing should be around 1 and 1.6, and the optimal value is 7.2. Okay, so yes, linear regression, because linear regression is a solved problem, we can do it very easily with linear model. But we can see, in other applications, if you're trying to minimize some function like the sum of squares residuals, if you create create a function to evaluate that function that you're trying to minimize. In this case, we create the prediction based on the parameters that we're trying to estimate, and we're going to calculate the sum of squares residuals. We can use the optimize function to search for these the solution here. Okay, so it searches the parameter space of beta 0 and beta 1. Are there any questions on this? It's okay. All right. So, well, then we'll see you guys on Friday. I'll try to at least have a good outline of what the final exam looks like by then, and then I'll discuss that on Friday, and then I'll release the actual final on probably Monday or something like that. Okay. All right. See you guys.